Good deal. All right, 4 more days to go, and it's all over. We are into chapter 16. Got a little bit more to go from 16, then a little bit of 17. Then I don't know how much more little we'll do at that point, but we'll see. All right, so in chapter 16, we're talking about acids and bases and pH. So we've talked about Bronsted-Lowry definition of an acid and base. And remember that a Bronsted-Lowry acid is a proton donor. A base is a proton acceptor. And remember that that creates conjugate acid-base pairs, which are related to each other by just that one H plus difference. Again, for them to be pairs, that could be the only difference there is. We talked about Kw, which is the concentration of H plus times concentration of OH minus, and that equals 1 times 10 to the minus 14. You can basically use this as one way to determine whether or not a solution is acidic or basic or even neutral. If the H plus concentration, again, is larger than the OH minus, that basically means the acid part is bigger than the base part. It would be an acidic solution. If the OH minus is larger than the H plus part, then the basic part's bigger than the acid part, and it will be basic. And if they do equal each other, it will then be a neutral solution. They both will equal 1 times 10 to the minus 7. Remember that the relationship that they have is as one goes up, the other goes down. So they kind of opposite relationship there. And again, if the H plus concentration goes down, OH minus concentration will go up. Now, the next thing we talked about was the pH scale. Remember, the pH scale runs from 0 to 7 to 14. Less than 7, again, acidic. Above 7, basic. And as we talked about, basically because of this situation here, 7 on the nose there is going to be neutral. And again, as you go from 7 to 0, you're becoming more acidic. As you go from 7 to 14, more basic. To calculate the pH, it is negative log of the H plus concentration. It does tell you in the actual name what you need. You need the H plus concentration to calculate it. We talked about your calculators as well as to which way to punch it in. Again, if you have a display calculator, just the way it's written. Non-display calculators, we talked about, pretty much got to go backwards in most of these formulas when you're punching it in. A similar scale to pH is pOH. It also tells you what you need to calculate it, OH, and that is negative log of the OH minus concentration. Remember that the pOH and the pH do run opposite of each other. So if you have a low pH, you have a high pOH, and vice versa. The relationship between those is the pH plus the pOH equals 14. So it does give you a little bit of options. If you maybe only know the OH minus concentration but want the pH, you calculate the pOH and then simply subtract 14 from it, and you'll have the pH by doing so. We also talked about that you can directly from the pH, you could directly from it get the H plus concentration. And to do so, the H plus concentration is the inverse log of the negative pH. Once again, on most people's calculators, that's going to be a 10 and a caret. Negative pH as to how you punch that in. Yeah. Yeah, it is. It is possible. Most of the time most of the time we do stay on the pH scale of 0. But you could have like a super acid, and there's one on the lab, I think. Or actually, there's a couple on the lab, I think, like that. But for example, if you had like a H plus concentration of 18, when you put it in there, you're going to get a negative number. So it is possible, sometimes referred to as super acids with a negative sort of pH. I would say more often than not, it'll be a positive number on that scale. But it is definitely possible to actually have a negative pH. Yeah. Other questions? Now we also can from pOH get directly from it the OH minus concentration. It's really the same calculation as the other there. Inverse log of the negative pOH. Again, 10 and a caret negative pOH. So this does give you, as we talked about last time, kind of a variety of ways you could solve these problems depending on sort of the pathway you choose. They all should really get you to the same end result if you do it correctly. But for example, if you have the pH and want the H plus, you don't even have to use KW or anything like that. You can just get directly from it and so forth as you go through there. A couple of things we also talked about, sig figs and concentration. So remember that the number of decimal places in like the pH, pOH type number is equal to the number of significant figures there is in the concentration value and vice versa if you're going in the opposite direction. If you have the pH, you want to go back to the concentration, decimal places to use sig figs when you do that. Any questions on any of that calculations there? All right, so we have a few more examples I think to do. So let's do some of these here. All right, so for each of these here, why don't we just do everything? It's just to make sure our calculators work. So let's calculate the pH, the pOH. So we'll do the pH on this one, the pOH. We'll do the OH minus concentration, and is it acidic, basic, or neutral? And same thing for the bottom one, pH, pOH. Okay, let's take a look, see how you're doing. We'll start with the first one here. We have an H plus concentration of 3.6 times 10 to the minus 9. I'm pretty much looking for everything. So really off the top of the bat here, you could do one of two things. You have the H plus, which means you can go directly into the pH equation and get the pH. Since we're also looking for OH minus, you could also use KW like we've done previously and get the OH minus. So you have a couple of options. I'm going to go right into the pH here though. So the pH is going to be minus the log of the H plus, and that's going to give me minus the log 3.6 times 10 to the minus 9. It's kind of like 8. And if we punch that in again correctly, we will end up with, in this case, a pH of 8.44. Again, at this point, I got a couple of options. I could get the pOH pretty easily. pOH would be 14 minus the pH. So that would give me 14 minus 8.44. And if I do that, then looks like 556 in terms of our pOH. Once again, here for the OH minus, I could still go with KW if I wanted to. I could also, because I do have now the pOH, I could do the inverse log of that. And that's what I'm going to do here. I'm going to go OH minus is equal to the inverse log of the minus pOH. And that would be, again, on your calculator, probably something that looks similar to that. And we will punch that in there. It looks like we will end up with about 2.8 times 10 to the minus 6 molar. Once again, we do need a concentration unit on it as it is a concentration. Once again here, alternatively, you could have used KW and you should have got the same answer. And that would be that the OH minus equals 1 times 10 to the minus 14 divided by 3.6 times 10 to the minus 9. And again, that should also give you the same number. So whichever way you want to do it should be good. This is a basic solution based off of the pH value. As we talked about a number of times last time, remember again, just one answer for that, and make sure you do look at the pH, because again, that is the scale most people have in their heads. So just look at the pH value. Any questions on any of those there? All right, then let's take a look at the other one there, which was we were given the OH minus. So again here, options, you can use KW to get the H plus. In this case, you could also just go right into the POH, and I could do that because I am given the OH minus concentration. So the POH here, negative log of the OH minus the log of 9.2 times 10 to the minus 2. And looking like a 1.04. Once again, probably the easiest thing at this point is to get the pH. That would be 14 minus the POH, and that would be 14 minus 1.04. Not one, 12.96. Looks good. 12.96 pH. Again, you could KW once again, in this case, you have the pH. So we could go directly from the pH there and go inverse log of the negative pH to get to the H plus. 10 and a caret. Make sure you make it negative 1296. And we'll do that there. Maybe hit the right button would be helpful. Try that. And punch in the right number as well. Going to give us a 1.1 times 10 minus 13 molar. Again, you also could have KW'd it as well, just like we did previously. And again, that should get you there as well if you like. Again, here, looking at the pH, 12.96 is basic in this case. Any questions on any of those there? Yeah. So like I said, you do have a little bit of variety of options as to how you want to calculate whatever you're looking for. And there's really no wrong way depending on whichever way you choose, as long as you, again, just punch it in correctly. Any questions on any of those there? Let's try a couple more here, maybe. All right, what is the POH? If you have the pH of this solution, why don't we also calculate the H plus and OH minus concentrations as well? H, which would be 14 minus the pH. So 14 minus 5.67. That's going to get us a POH in this case of, looks like 8.33. At this point, probably you need to do some inverse log. So since you have the pH given to you, inverse log of the negative pH. So 10 to the caret negative 5.67 will give you your H plus concentration. And that's going to be, looks like 2.1 times 10 to the minus 6 molar. Again, at this point, you could use KW if you wanted to. You could also use the POH. Just to mix it up, I'll use a KW here. Why not, for old time's sake? We go 1 times 10 to the minus 14 divided by 2.1 times 10 to the minus 6. And that's going to get me here, should be like 4.8 times 10 to the minus 9 molar in this case. This solution would be acidic because of the 5.67 pH. Any questions on any of that? Yeah. Are you asking on what, on like the concentration numbers? Is that what you're asking, or? Yeah. So in this particular case, the original number here, the pH, went to 2 decimal places, which means when we turn that into a concentration, we should have 2 significant figures. Yeah, so when we go from concentration to pH, it's sig figs to decimal places, and when you're going backwards, it's like decimal places back to sig figs. Yeah. Other questions? No. Okay. And at that point, that's why we maintain the 2 here as well. Yeah. All right, let's see here. One last one here. We'll just do what it asks. The pH of the solution is 3.14. What is the H plus concentration? Okay, so again, here we have the pH. And as I mentioned before, directly from it, it tells you, you pretty much get the H plus. And it is that inverse log of the negative pH. Again, on your calculator, most people's the second or shift button, the log button, the negative button, and your pH entered in there. Should look something like a 10 and a caret, negative 3.14. And that's going to get me here like a 1.38 in this case. Any questions on that one there? All right, so obviously you need to be able to calculate pH, pOH, H plus, OH minus concentration if you're given a variety of obviously information. All right. So let's talk then about what happens when we have the pH of a strong acid. So remember that we talked about kind of 6 strong acids. And again, a reminder that those strong acids, hydrochloric acid, nitric acid, perchloric acid, sulfuric acid, hydrobromic acid, and hydriodic acid. Remember, some strong bases are group 1 and 2 on the periodic table that has hydroxide in it, like sodium hydroxide, potassium hydroxide, calcium hydroxide, etc. So what these both have in common is, as we talked about, they are strong electrolytes, which means they're going to 100% break apart in solution. So when we have a acid like hydrochloric acid, we know that when that kind of goes for a swim, if you will, it will completely dissociate in that solution into H plus and Cl minus. So when we're thinking about the pH, the important one is actually the H plus concentration, as that is what affects the pH. pH is equal to minus the log of the H plus concentration. So that's really important. If the concentration of H plus is high, we will have a relatively low pH, and vice versa. If you have a lower H plus concentration, you'll have a higher pH because you also have a higher OH minus concentration. So let's say, for example, we had 0.1 molar hydrochloric acid solution and we wanted to know the pH. So sometimes you may not be given, kind of like what we've been given so far in this chapter, like a generic H plus concentration or OH minus concentration or, H3O plus concentration. You may actually be given a formula for an acid or a base. And in this case of the acid, we know it's a strong acid. I would say for our purposes here in this class, if you're given a formula for an acid or a base, it is probably safe to assume that's a strong acid or base for this application, because weak acids and bases is a much longer calculation that we don't talk about here. So, it's probably going to be a strong acid or base if you see it in this class. When you get to like 1B, you'll have weak acids and weak bases you deal with. So when we look at this, because this acid is a strong acid, it's going to break apart into H plus and Cl minus. Now, as I mentioned before, it is the H plus concentration that's really the most important here in terms of the pH. And if you remember when we talked about concentration and ions, we could just kind of do like a stoichiometry relationship. It is a 1-to-1 relationship between those two, which means the concentration of the H plus in this solution would also be 0.1 molar. And because of that, now I have the H plus concentration, and now all I have to do is go into my pH equation, and I can actually calculate the pH of it, minus the log of 0.1 molar in this case. And that's going to get me my pH there of 1, which is acidic and what we would expect to happen. So if you're given a formula of a strong acid, the good news is also if you look at that list of strong acids, pretty much most of them are monoprotic, which means they have just one hydrogen, which means whatever their concentration is of the whole thing will most likely be the concentration of the H plus concentration. So you're kind of given the H plus concentration. Now, the same thing can happen, for example, if you are given a base. And let's just say we have the same thing here, a 0.1 molar sodium hydroxide solution, and we wanted the pH. The difference, though, is when you're given a base is this base is going to break apart 100% into a sodium ion and a hydroxide ion. So in this case, to help us get to the pH is actually the hydroxide concentration we're interested in. And we could do the same thing. This is 0.1 molar. It's a 1-to-1 relationship between those two, which means that this guy is 0.1 molar. The difference, though, is because this is a base, we cannot get the pH from it because we have the OH minus concentration. So we could get the POH first, which is minus the log of 0.1. And that will give me a POH of 1. And then we can subtract our 14 and get our pH of 13, which makes more sense as we're talking about a base in this case. So if you have a strong base given to you, you pretty much want to figure out the hydroxide concentration. That will allow you to get to the POH and then subtract 14, and that'll get you to the pH. If you're dealing with a strong acid, that will give you the H plus, and you go right into the equation and get the pH basically directly from it. Any questions on that there? So again, the good news is in this class is if you're given a formula, it's probably strong and it has to calculate the pH because we definitely don't talk about weak acids or bases calculations here. Okay, let's take a look at this. So again, we got a formula here. We have perchloric acid, which is one of those strong acids. So we do know that this is going to completely break apart 100% into H plus and perchlorate in this case. Once again here, it is the H plus, which is of interest to us. Again, it's a 1-to-1 relationship between these. And that means that the concentration of the H plus would be 0.025 molar. That's really all we need to go into our pH minus the log of 0.025. And that's going to get us here a pH of, looks like 1.60 in this case. Any questions on that one there? Looking at the second one, I see hydroxide, which tells me it's a base. I also see it's hooked up with somebody in group 2, which probably tells me it's a strong base. So remember, your strong bases there is kind of group 1, lithium, sodium, potassium, hang a right, calcium, strontium, barium. Any of those guys kind of hooked up with OH in the formula is most likely going to be a strong base. So because this is going to be a strong base, it will also break apart. It's going to break apart into a calcium ion and a couple of hydroxide ions in this case. And once again here, 0.025 molar is a 1-to-2 relationship. In this case, we are interested in the hydroxide. And because it is a 1-to-2, we do have to multiply the concentration by 2 to get the proper hydroxide concentration. That would be 2 times 0.025. That gives us a proper hydroxide concentration of 0.05 molar. That then would go into our POH as we have the hydroxide concentration given to us, minus the log of 0.05. Looks like a 1.30. Once again here, the pH can be found by taking 14 minus the POH, and that's 14 minus 1.30, I believe. And that looks like we end up with, guess it'd be better to put the right number in there. Try that again. 12.70 pH. And that does make sense as this is basic. And that definitely is a basic pH. So if you're given a formula, you just got to get the H plus or the OH minus concentration. I will say, as I mentioned earlier, because most of the strong acids are monoprotic, probably the only one you might have to worry about adjusting concentration is probably the base. If you get something like we have in this problem here. Question on that one there. All right, the last thing we're going to talk about in this chapter are buffers and a buffered solution and sort of what a buffer is. So a buffer is a solution that can resist changes in pH even when you add additional acid or base to it. So sometimes people have a misunderstanding about what a buffer is. Sometimes people think a buffer is a neutral solution, and it's not necessarily a neutral solution. It can be a neutral solution. You could also have a buffer that's an acidic solution, and you could have a buffer that's a basic solution. You could actually make a buffer at any pH you choose. So pretty much can make an acidic buffer, you can make a basic buffer, and you could have a neutral buffer as well. But what the buffer is able to do is it's able to maintain the pH of where it started at, even if you decide to add additional acid or base to it. So for example, if you started with a buffer that had a pH of 4 and you added some acid to it, the pH would remain near 4. Would it go down a little bit? It would. It'd probably maybe go from 4 to maybe 3.9 or something like that. But it won't go from like a pH of 4 all the way down to like a pH of 1. So you won't have this really big jump in pH. Just like if you have that buffer that started at a pH of 4 and you added base to it, you would see the pH maintain around 4. Again, maybe it goes up a little bit, but it will not go from like a pH of 4 all the way to like a pH of 12 or anything like that. So a buffer is able to resist changes in pH. The reason a buffer is able to do that is actually what it is made out of. And a buffer is made out of a weak acid and the conjugate base, are sometimes referred to as the salt of its conjugate base. Or you can make a buffer out of a weak base and the salt of its conjugate acid. You cannot have a buffer that is made out of a strong acid or a strong base. So you cannot have a buffer that is made out of a strong acid or a strong base. So it does need to be weak. They do need to be partners. And by the way, the partners here are the same thing as Bronsted-Lowry partners. The difference between these guys is that 1H plus. So the only thing between these two is the difference of 1H plus. Now, because it is made out of either a weak acid or a weak base, what that is able to allow to happen is when you make a buffer, you're able to keep the acid part of the buffer and the base part of the buffer in solution because it's a weak acid or weak base. So that's the acid part of the buffer, and that is the base part of the buffer. They both are actually in the solution to begin with, and that is what gives it its function, is both of those things are swimming around in there. And because they're a weak electrolyte, it will set up this equilibrium. For example, if you made a buffer of HF and NaF, that is hydrofluoric acid and sodium fluoride. That is a weak acid, and this is the salt of its conjugate base. What is actually the buffer components here is the HF and the F minus. These are really the two buffer parts. The HF obviously comes from the hydrofluoric acid. The F minus comes from the sodium fluoride. And that is why it's referred to as a salt, because it has a sodium hanging out there doing nothing. It's really just a spectator ion, basically. But that is why it's referred to as a salt of its conjugate base. And that means that when you set up that equilibrium, the HF, because it's a weak electrolyte, will set up this equilibrium here. And once again, you now have the acid part in there. You have the base part of the buffer in there. And you have both of them floating around ready to work. The reason you cannot make a buffer out of a strong acid or a strong base is if you try to make a buffer out of, say, HCl and Cl minus, those two things are related to each other, even if you want to use sodium chloride. The problem, though, is the hydrochloric acid is a strong acid, which means when you go to put that into your beaker, it is not going to stay together. It's just going to break apart completely into H plus and Cl minus, and then you'll have some more Cl minus in there. And now all you'll have in this buffer, with air quotes, is basically just the base part. You will not have the acid part there because the HCl completely breaks apart. So because a strong acid or a strong base will completely dissociate and break apart, there's no way to keep both the acid part of the buffer in solution and the base part of the buffer in solution at the same time. And a weak acid or a weak base could do that because it sets up this equilibrium that kind of keeps them both floating around in the solution together. So like HF, sodium fluoride, everybody's other favorite example of a buffer, acetic acid and sodium acetate. Again, the buffer part of this is the acetic acid, and the acetate part is really the functioning part of the buffer. The sodium there, again, it's just to balance out the charge, not doing anything. But the sodium acetate is referred to as a salt of its conjugate base because it has a sodium in there. Any questions on that there? So let's talk about how it's able to really function. So let's take first off what happens if we were to add acid or base to a non-buffer situation. So if we added an acid and base to a non-buffer, let's take everybody's favorite non-buffer, which is water. Yeah. So water is not a buffer. And if we added some hydrochloric acid to water, what's going to happen is this. If I add HCl to water, so I got me some water over here, and I decide to dump in there some HCl. Because it's a strong acid, as we've been talking about, it will 100% break apart into H plus and Cl minus. You'll have 100% of these ions. You'll have none of these still together. And what's going to happen is this thing is just going to break apart into a bunch of H pluses and Cl minuses. Now, the important thing that we see at this point is what we just did to this solution is we just added a ton of free H plus to that solution. And that's really problematic because as the H plus concentration increases, the pH will decrease a lot in this case. So because we influxed into here a bunch of free H plus, the amount of H plus goes up in that solution really, really quickly. The result of that is the pH drops really, really quickly in this case. And we would see a really big jump in pH, really drop in pH, I guess, in this case. Let's just say our deionized water was 7 in terms of this pH where it started. Maybe it goes from 7 down to like a pH of 2, a really big jump in pH because of that big influx of H plus really, really quickly in that solution. It's going to cause a major effect on the pH. Hence, water is not a buffer because you will see that occur. You will see that pretty big drop in the pH. Now, let's just say we added some sodium hydroxide to water, which again is not a buffer. So if I had some water over here and I add some sodium hydroxide, that is the source of sodium ions and hydroxide ions I want to dump in there. Once again, because sodium hydroxide is a strong base, it is going to 100% break apart into our sodium ion and hydroxide ion. And much like above, 100% of what we're going to have is that. So we'll have a bunch of sodium ions, which is not going to do much to the pH, but will really affect the pH at this point is the amount of free OH minus. So by adding this base to water, we have now added a bunch of free OH minus. And that's problematic because the concentration of OH minus definitely went up. And because H plus is tied to the concentration of OH minus, the concentration of H plus will go down a lot. And the result of that is our pH will actually spike up a lot. So in this case, we may start at a pH of 7. You may add some sodium hydroxide to it because you've now added a lot of OH minus in that solution really quickly. We may see the pH go from like 7 to 12 or even higher. We see a really big, big jump in the pH. First off, any questions on what happens in a non-buffer situation? All right, so then let's talk about what happens if we add these exact same two things to a buffer. And we'll use a different buffer than everybody else likes to use because I don't feel like writing acetic acid and sodium acetate. We'll actually use this hydrofluoric acid and the sodium fluoride buffer. So this is going to be our buffer. Again, a buffer has a acid part, which is this guy, and it has a base part, which is this guy. Once again, the sodium here is really not doing much. The actual functioning part of this buffer is the F minus, is actually the functioning part or the base part of the buffer. And again, as I mentioned before, what makes something a buffer is that Bronsted-Lowry definition in a sense. We have this guy, and again, the only difference between those two is 1 H plus difference. So again, those are kind of two things you want to look at when you're like, can this be a buffer or not? You want to make sure that they are related to each other, just like Bronsted-Lowry, between differences only 1 H plus. And you also, as I mentioned earlier, need to have something that's either a weak acid or a weak base and its conjugate partner. So when we set up this buffer, we will have a solution here that will, because it's a weak electrolyte, set up this equilibrium where we basically have this floating around in solution. And this again is our buffer. And once again, that is our acid part of our buffer. And this is our base part of your buffer. So now in this case, when you take your HCl and you want to dump it into here, which again is a source of H plus and Cl minus, we are actually going to get a reaction that's going to occur. So when I take my HCl and I dump it into my buffer here, will my hydrochloric acid react with the acid part of the buffer or the base part of the buffer? It will react with the base part of the buffer, right? Because they're called acid-base reactions. So when I add HCl to it, it'll actually react with the sodium fluoride, which is actually the base part of the buffer. This is a double displacement reaction that's going to happen. We're going to swap some partners here, basically, and that will make some sodium chloride and some HF in this case. So we see a couple of things are formed. We see this guy, which is a salt, and it's actually a neutral salt, which means it will not affect the pH. We actually see this guy made, which is actually part of the buffer to start with. So we actually make some more HF in this reaction. And that's very common when you have a buffer. What will happen is part of the buffer will react with whatever you're adding, and it will actually go and make the other part of the buffer. So you kind of use a little bit of the buffer up, but then you make the other part of the buffer as well. But it is more important, actually, in this case, what we do not see here. It's actually what we do not see here that we did see when we added the acid to water. What did we see when we added the acid to water that we do not see when we added it to the buffer? When we added the acid to the water, what did we make? A bunch of H plus, right? We made a lot of free H plus in that solution. When we added that same acid to the buffer, we did not make any free H plus from that incoming acid. And because of that, what that will do is the concentration of H plus that we started with will remain relatively constant. And because the H plus concentration stays relatively constant, the pH will also remain relatively constant as well. I say relatively constant because if you're actually following the pH, you will see the pH move a little, and it will move a little bit downward in this case because we're adding acid, but it will not have a really big jump in the pH. So it will not have this really big drop in the pH, but it may go down a little bit. So this will be like, it went from like 4 to like 3.9 or something like that. So a small little drop, but not a really big drop. And that is because what is happening in this case, when you add the H plus in here, instead of being allowed to be free, it will go and find the F minus, and they will tie up and make some HF. So that H plus that normally would be just floating around freely in the solution gets tied up, and now because it's not freely floating around, it allows the H plus concentration that was originally there to basically remain about where it was, and that's what's able to maintain the pH in this case. Question on that there. Now, what happens if we add the base to this buffer? So let's do the same thing here. So we have our buffer beaker. Again, it's going to set up that equilibrium where we have, again, our acid part of the buffer, our base part of the buffer. And in this case, we're going to add some sodium hydroxide in, which obviously is a source of sodium and hydroxide ions. So when we add sodium hydroxide to the same buffer, the sodium hydroxide, which is a base, will react with the acid part of the buffer, which is the HF. And it will do just a basic acid-base reaction. It will make water and a salt, NaF. Again, also double displacement basically here happening. So in this case, we made water, which is neutral, so that's not going to screw up the pH. We also made more of the buffer. In this case, we made some more of the sodium fluoride. It once again is what we do not see here. that we did see when we added it to water. And if we go back and look at what happened when we added it to water, we produced a bunch of OH minus really, really quickly in that solution. And here we are not producing any free OH minus in this solution. And because of that, the concentration of OH minus stays relatively constant. And because H plus is attached to that, basically, the H plus will stay relatively constant, and thus the pH will also remain relatively constant as well. So here, when you add a base to a buffer, it prevents the formation of free OH minus in that solution, and that's what's able to maintain the pH. So when you added this OH minus, goes and finds the HF and makes water, and the result of that is you actually make some more F minus in that solution, but the result is you did not make any free OH minus. So the way a buffer is able to maintain pH is because it has an acid part and because it has a base part in the solution to begin with. When you go and add additional acid or additional base to your buffer solution, it prevents the formation of free H plus in the solution and really free OH minus in the solution. And by preventing the formation of free H plus or OH minus, it's able to basically maintain the H plus concentration and thus maintain the pH about where it's at. Again, here, if you're following the pH, you would see the pH go up a little bit, but again, not a giant jump where it's up because of that question on that there. So in general, if you were to make a buffer, a lot of times you would make the acid part of the buffer and the base part of the buffer kind of equal to each other. So if you made a buffer and it has like an acid part and it has a base part to the buffer, as we saw, when you add some acid to it, it will react with the base part of the buffer and it will use up some of the base part of the buffer, but it will make some of the acid part. So you'll make some more of the acid part of your buffer when you do that. You'll use up some of the base part of your buffer. And same thing here. If you add base, it will react with the acid part of the buffer, and you'll make more of the base part of the buffer here. So you'll make more of this. And again, that's why a buffer can maintain a pH over a good period of time because it's kind of regenerating in a sense. You use a little, but you make a little bit more of the other. So it kind of regenerates itself as you're doing it. There is a limit to how good a buffer is. It is really important when you make a buffer that you make it with the right concentration and also the right molarity based on the acid and base that you may be adding. For example, if you didn't follow instructions and you decided to just keep adding acid, every time you add acid, you're going to chew up some of the base part, right? You're just going to kind of keep chewing up the base part, keep chewing up the base part, keep chewing up the base part. At some point, you will chew up all of the base part. And if you continue to add acid at that point, now all you're doing is jumping a bunch of H plus in there really quick. You're going to see a really big drop in the pH at that point. Same thing over here. You know, if you add base, you're just going to keep eating up the acid part, eating up the acid part. At some point, you'll have no more acid part to handle that hydroxide coming in. And you'll see a really big jump in the pH. By the way, that is exactly what happens at your equivalence point in your titrations. You actually make a buffer in that acetic acid titration, and then you blow through the buffer by continuously adding the sodium hydroxide. And if you remember, right, the indicator can jump color really quickly, and that's because the pH will jump really high as you blow through the buffer part of your solution you made as you're doing your titration, and that's why you get that really big jump in pH that goes vertical near the equivalence point, and that's exactly what's happening. Also, if you grab the acid or base that's way too concentrated for your buffer, so if you made like a 0.1 molar buffer and you grabbed like 18 molar hydrochloric acid and you added a bunch of it to it, it's just going to blow right through it because you don't have enough in your buffer to handle it. The moles of your acid in your buffer and the moles of your base in your buffer is really what's important because that's what's there to react and prevent the formation of free H plus or OH minus. Any questions on a buffer, how it works? Sometimes we use buffers in laboratory, for example, if you're doing like work, say, on the protein or something like that, maybe you want to do it under the right, say, pH conditions, right, of the environment it's in. You could take your protein, put it in a dialysis bag, make a buffer at a specific pH, let it sit in there, and it'll equilibrate to the same pH environment as, say, in the body or something like that. So sometimes we use buffers for that. By the way, buffers are really good in the sense that you can really make it at any pH that you want. And because they resist really big jumps in pH, when you actually go make a buffer, usually the buffer is not exactly the pH you want. And because it doesn't change really drastically when you add acid or base to it, you could actually take like a strong acid or strong base and just put some drops in there, and you could actually dial in your buffer to the exact pH that you want because you could literally watch it go up, 0.1, 0.2, very slowly rise in the pH or drop in the pH if you need to lower it. So you could actually make your buffer and then usually use acid or base to kind of dial it into the exact sort of pH that you want. Any questions on how buffers work there? All right, that is chapter 16. Okay, we're going to continue on here. Chapter 17, equilibrium, final chapter. So we're going to talk about some things out of this chapter here. But equilibrium in general deals with a certain type of reaction, one that we kind of saw before when we were talking about sort of weak electrolytes. So equilibrium in general, whoa, disappears. Try that again. All right, take two maybe. All right. All right, so it involves a specific type of reaction, which is this type of reaction here. Was sometimes referred to as a reversible reaction. And a reversible reaction, much like we see with weak electrolytes, have those arrows that head basically in both directions. And what that means is when we talk about a reversible reaction like this, there's sort of two directions that we talk about. Going from reactants to products, that is what is sometimes referred to as the forward direction. And what happens in these type of reactions is at some point you will actually make enough products that the products will decide they would like to recombine and head in the opposite direction, and they will go towards the reactants, and that is what is known as the reverse direction in a reaction. Now, eventually what will happen is this reaction will come to what is known as equilibrium or chemical equilibrium. And sometimes people have a misconception about what equilibrium means because the word equal is in there. So people think it means that you have equal amounts of everybody kind of on both sides of the arrow. And that's not what chemical equilibrium means. When a reaction like this reaches equilibrium, what we're actually referring to is the rate of the forward direction will actually equal the rate of the reverse direction. And that is really what sort of equilibrium means. And basically the consequence of that, as we'll talk a little bit about in this chapter, is what it will essentially do is lock everybody into place in terms of their concentrations. So just as quick as it goes to the product side, it will go back the other way to the reactant side. And that means whatever concentrations everybody has, they pretty much will be able to maintain those concentrations indefinitely. If you're dealing with pressures, it will also lock the pressures into place basically, and they won't change over time. Now you could do something to it to screw it up, but one of the nice things about these type of reactions are they are sort of, if you want to think about it, self-correcting. So you could do something to this type of reaction to screw it up, and it would no longer be at equilibrium, but it will self-correct itself to get itself back to like an equilibrium state. So it's one of the interesting things about these reactions, which is you can really just screw it up, but it will really try to self-correct itself and get it back to that sort of equilibrium situation. So to deal with a little bit of that, we're going to talk a little bit about a reminder how sort of chemical reactions occur. Remember that in order for a chemical reaction to occur, we really need a couple of things to occur. One of them that's kind of important is you do need some type of collision to occur between reactant molecules, right? So they have to kind of collide with one another. They do have to collide with one another with the right amount of energy and also in the correct sort of spot. Now, the rate of how fast a reaction will occur depends on the concentration of reactants and also temperature. But not all collisions that occur between reactant molecules will actually lead to products being formed. But that does need to happen. We will get this sort of collision that occurs. We'll get some separation of these bonds, and we'll start making some new bonds while breaking some old bonds along the way until we get to our products basically being made in this case. Now, one of the things that can affect how fast or slow a reaction takes place is concentration and temperature. When we increase the concentration, that usually leads to a faster rate, and that is really just because of availability of reactants, for example. If we increase the concentration, we basically have more reactant molecules, for example, there, and they could come together and make products. Or even if you added more products, you could then make more reactants and so forth. So the availability of those guys to find each other quickly will increase the rate of reaction. In addition, temperature is a really big, important thing in terms of increasing the rate of a reaction. When we increase the temperature, everybody has more energy. And with more energy, that allows everybody to get to the other side. One of the things that we saw in chapter 10, right, was those energy diagrams, if you remember. We have our reactants and our products. We have that activation energy, which is the hill that the reactants has to climb to get to the other side to make products. And remember that the bigger the activation energy hill, the slower the reaction usually, because there's less guys that can get up and over the hill. But when you increase the temperature, you get a greater proportion of reactant molecules that have enough energy basically to get up and over to the other side. And that usually results in really the reaction occurring faster. That is also why the opposite is true. If you decrease the temperature, usually the reaction rate will slow down, because when you decrease the temperature, you're removing energy, and now what happens is you have a smaller amount of reactants that can get up and over to the other side to make your product. So it can affect one way or the other. If you remember, again, when we get to the very top, that is the transition state. And here we have things that are partially made bonds and partially broken bonds, and it will very quickly kind of drop to the other side. One of the ways that we could speed up a reaction that we also talked about is by adding a catalyst. And a catalyst, again, is not a reactant. It's not a product. It is there simply to speed up the reaction. In most cases, it's there to find a much better alternative, more efficient pathway for that reaction to take place. Ultimately, when you add a catalyst, because it's able to find that alternative way for that reaction to occur, a more efficient way, it actually will lower this activation energy hill. So instead of your reactants normally having to come up and over here with the catalyst there in that better pathway, they only got to climb that high. And that again is going to allow more reactant molecules enough energy to get up and over to the other side. And the result of that is you usually will see again an increase in the rate of a reaction. So when we talk about equilibrium, that's when two processes are happening at the same time. Another place where we see equilibrium happen a lot is what we talked about with like phase changes, like at the normal melting point and say boiling point. If you remember at water at 0 degrees Celsius, you have solid and liquid occurring with each other. They're actually at equilibrium with each other. That's why we talked about you have like ice crystals happening at that point. You got a little bit of solid ice, you got a little bit of liquid water happening, and they're in equilibrium with each other. And same thing at 100 degrees Celsius as you go from liquid to gas and gas back to liquid for water. We have a little bit of both phases happening in equilibrium with one another. Now, when something reaches chemical equilibrium, like I said, it may appear to you that the reaction is over. So, for example, you may mix some things together and this reaction may hit equilibrium and your beaker may just look red, right? Maybe it wasn't red to begin with, but it turned red, for example. And when you look at it, you may go, well, this reaction's over. It already turned red. There's not much happening. It's still red. The reaction's over. And in an equilibrium reaction on the macroscopic level, it may look static, like nothing's happening, but there is a lot of activity happening on the microscopic level to, for example, maintain that red color that you see. So, for example, if this reaction was A plus B goes to C plus D, if you were to zoom in, you would see a lot of guys going this way, a lot of those guys coming back this way, a lot of activity sort of happening, even though when you just look at the big picture, it looks like nothing much is happening. So that is something that sometimes people have a hard time with in terms of equilibrium. They think, it's sort of over when something happens, but it's actually a lot is happening just to maintain what you're looking at. And that again is because these are reversible reactions. You could think of it like a two-way street, it's going forward and reverse. And that's different than a non-reversible reaction where it essentially is just a one-way street, why we have one arrow heading towards the product side. Everybody's dumping out on the product side. Nobody's coming back the other way in those type of reactions. Now, when it does reach equilibrium, as I mentioned before, it does not mean that you have the same amount of everybody on each side, but it will lock everybody into place. And as you can see here, initially we have all reactants, no products. As this reaction occurs, we use some of our reactants to make some of our products. Then we now have less reactants, more products. And eventually, though, as we see, we still have reactants and we still have products. But what we see now is everybody's concentration has basically leveled out and has stopped changing. And this is when chemical equilibrium has been reached. This guy maintains 2s, these guys maintain 5s, and they will continue on that path indefinitely. Again, like I said, unless you go do something to screw it up, and then they'll come fix itself anyways along the way. Now, graphically, if you were to look at a graph, where that happens is where everybody's lines pretty much just plateau out and level off. So here's the rate of the forward direction, which usually at the beginning will occur. We'll start having our reverse reaction starting to occur at some point, and everybody's rate will basically flatten out. and that is when chemical equilibrium has been reached. So concentrations reach levels where the rate of the forward reaction equals the rate of the reverse reaction, and that again is what chemical equilibrium means. Um, Now, something else is kind of interesting is you can start these reactions, for example, any way you want. And what I mean by that, for example, is you could start like the example we just saw on that slide with all reactants and no products. You could also start one of these reactions with all products, no reactants. You could start with a little bit of reactants, a little bit of products, and they will all come to rest basically at equilibrium. So sometimes people think you always got to start maybe with the same amount of something. It doesn't really matter. You can start with all reactants, start with all products, start with a little bit of everybody, and eventually that rate of that forward reaction will equal the rate of the reverse reaction. So let's take a look at this sort of equilibrium here. We have water plus some CO, make some H2 and CO2. So let's just take a moment here and you think about it. If we have this system at equilibrium, and we got a little bit of everybody in there, obviously, at this point, what would happen to the concentration of everybody if we added more water to the mixture? So take a moment and for each of these things, decide, will their concentration go up if you add more water? Will the concentration go down? Will it stay the same? So take a moment or two and see what you come up with. Which side of the arrow is water on? And in this case, water is over here. So we would be like adding more water in this case. We would essentially be adding more reactants. And what that's going to do is because we now have more reactants than products, it will kick off actually the forward reaction. And it would kick off this reaction heading in this direction because of the availability of all of our reactants in this case, right? So one of the things we just talked about was sort of the rated reaction rate based on concentration. The availability of all these reactants is going to allow the reactants to find each other quicker, and it's caused that forward reaction basically to occur. The result of that is we actually should start to make more products in this case. And in terms of the concentration of our products, we would expect the H2 should increase. The CO2 would also increase in this case. Now, the CO in this case should actually start to decrease. And that is because reactants are necessary to make the products, right? The only way you can make the products is both of those reactants has to come together. Now, what happens with water in this case? Well, water is kind of a weird one in a sense because what's truly going to happen is water is going to go up, and it's only going to go up because you added it yourself. So you like artificially inflated it. But what happens is you'll see a jump in water, but when water and the CO start to react, you will then see the water start to come back down as well. It may actually end up higher than it started with only because you added it. You kind of artificially raised it. But overall, what will happen is the H2O should start to come back down as it's reacting with the CO in the forward direction. And again, that should increase our products in this case. Any questions on that? So really when you have a reversible reaction like this and you do something to it, really what you want to think about is, am I like increasing the forward reaction to occur? Am I like increasing the reverse reaction to occur? That's sort of what you want to think about. So let's take a look then at another, come here, maybe. Try it again. Maybe I found it. There we go. Let's take a look at the same reaction. What will happen to everybody's concentration if we add H2 instead of H2O? So in this case, what should happen to everybody's concentration? Should it increase? Should it stay the same or decrease if you added H2 to this equilibrium? So again, take a few moments and think. Okay, so now in this case, we're adding H2. and H2 is over here, actually on our product side. So sort of the opposite thing's going to happen in this case. Because we added H2, which is a product, we now actually will have more products available than reactants. And what that's going to do is actually kick off the reverse reaction to occur, again, based on the availability of products being available to react with each other. That should cause that reverse reaction to occur. That means that our products will combine to make our reactants, and that means that we should expect to see an increase in the amount of our reactants in this case. We once again here will see a decrease in our product there, our CO2, because it's necessary to make our reactant. And for the H2, once again, we will see a similar thing we just talked about. It will artificially go up because you added it. But once it starts reacting with the CO2, it should start to come back down at this point. Once again, it may end up higher than it started with just because you artificially added it in. Any questions on that there? Okay. All right, then let's talk about one way that we express an equilibrium, and that is what is known as the equilibrium constant. And the equilibrium constant is abbreviated with a capital K. And there's all kinds of equilibrium constants. We've actually just saw one in the previous chapter. That is what is known as Kw. That is an equilibrium constant. An equilibrium constant is found by taking the concentration. So again, when you see that, that is concentration, and that typically is molarity of your products divided by your reactants. So it is the concentration of your products divided by your reactants. You do need to take into account the coefficients. They become the exponents here. So the coefficients here become the exponents. There is all kinds of K values that you'll learn about. Again, pretty much Chem 1B is brought to you by the letter K. You learn about every single K value you probably never want to know about, but you learn about them all pretty much in there. Now, K is one of the few things in chemistry that actually does not have units. So the value of K is just a number. So K is just a number, no units. Now, what does K tell you? Well, K can tell you a couple of things. If you have a large value of K, that means that when you reach equilibrium, you should mainly have products. If you just think about it mathematically, if I have a big number on top divided by a small number, that's going to give me a big number. And if you have a small value of K, when you reach equilibrium, you will mainly have reactants. What's considered a large value versus a small value? The large value of 1 is considered large. So anything 1 and above is considered large. Anything less than 1 is considered small. There is variations of that. You could have really, really large values of K, like times 10 to the 54. You could have really, really small values of K, like times 10 to the minus 36, and you could have K values anywhere in between. K values are constant values, and the only thing that affects it is temperature. So temperature is the only thing that will affect the actual value of the equilibrium constant. And what I mean by that is this. Let's just say, for example, you did 3 experiments at 25 degrees Celsius and you had this reaction like A plus B goes to C. And in experiment 1, You did, all reactants, no products. Experiment number 2, no reactants. You started with all products. Experiment number 3, you had a little bit of everybody, some reactants, some products. Every single one of those experiments at 25 degrees Celsius, if you calculated the equilibrium constant for it, it will come to the same number. And it should come to the same number. Again, even if you started with all reactants in one or all products in the other or a little bit of everybody, the ratio of products to reactants at 25 degrees would give you the same K value. Now, if you did the exact same 3 experiments, but it was at 40 degrees Celsius, and you ran the exact same 3 experiments, but the only difference was you did it at 40 degrees for those 3 experiments. You could calculate the K value for each of those experiments, and they once again would be the same value at 40 degrees. But if you compared the K value for those experiments at 25 degrees to the K value at 40 degrees, they would be different numbers. So that's what we're talking about when we talk about the temperature changing. If you keep the temperature constant, you run as many experiments as you want, the K value should always end up being the same ratio. But if you're comparing it from like one temperature to the next, you will have a different value of K for it. You may be asking, how is that possible if it's products over reactants and you start with different amounts in each reaction? How could they all hit the same number? So a very simple way to think about it is like this. Let's say I wanted my equilibrium constant to be 2. I could get 2 by taking 4 divided by 2 is 2. 8 divided by 4 is 2. 2 divided by 1 is 2, right? Those are all different numbers. They're all different ratios, but they all come to the same end result, right, of 2. And that's what happens in this thing. Even though you're starting with different amounts, when it comes to rest in terms of the ratio of products to reactants, it will always come to the same ratio as long as the temperature stays the same. If you change the temperature, then you'll get a slightly different ratio of products to reactants. Any questions on that there? All right. By the way, as well, when you calculate the equilibrium constant, it does need to be equilibrium concentrations that go in there. So they can't be initial concentrations. It has to be equilibrium concentrations that go in there. So for example, here, if we were going to write the equilibrium expression for this reaction, like we see down there, we would take our products, which is our NH3. So the concentration of NH3, because the coefficient is A2, we would have to square it, divided by the concentration of N2. Again, here the coefficient is 1, so we don't have to put anything on it. Times the concentration of H2, coefficient is 3, so we do have to cube it. Excuse me. By the way, this is what is sometimes referred to as the Kc value. C meaning we did it with concentration here. We would be using the molarity of each of those things at equilibrium to put in it. So sometimes people refer to this as the Kc value, again, C for concentration. By the way, you could do this as those are all gases. We sometimes, when we deal with gases, look at pressures. So you could actually write an equilibrium that involves pressures. That would be the partial pressure of NH3 squared divided by the partial pressure of N2 and the partial pressure of H2 cubed. Those are pressures, so sometimes that's referred to as the Kp value, P meaning that you did the calculation in pressures rather than C for concentration. So sometimes you'll see those little subscripts on the bottom, and those little subscripts on the bottom tell you some information about it. Again, we saw Kw earlier. W is the ionization constant for water. There's, for example, a Ka value. A has to do with an acid, a weak acid. There's a Kb values, which it will deal with bases. So the Ks, they're all the same, really. They're all just products over reactants. But you'll sometimes see different little letters or symbols at the bottom to indicate what it is dealing with. Any questions on that there? Now, there are a couple of things that we typically do not include in the equilibrium expression. We do not include anything that is a solid or a liquid. So those two things are not included in the equilibrium expression. The things that we do include are pretty much what's left, which is things that are aqueous or things that are gases. So those are the two things that get included. So if you come across a reaction where there's something that's a solid, you would not include it in the expression. And if you have something that's a pure liquid like water in a liquid state, you would not include that either. Now, K, as I mentioned before, always has the same value at the given temperature, regardless, as I mentioned earlier, if you start with all reactants or all products, a little bit of everybody. The reaction at a given temperature, there are many different equilibrium positions, but only one K value. And the equilibrium position is set by the equilibrium concentrations. So let's take a look at this one here. We want to write the equilibrium expression. Once again here, our K would be our products. So we have the concentration of H plus times the concentration of acetate divided by our reactant, which is our acetic acid. And again, that would get us our equilibrium expression in this case. All right, so for the reaction below, we want to calculate the value of the equilibrium constant given the concentrations. So let's go through how we would do this. So these are equilibrium concentrations given to us. So we would take our equation, our reaction here, and we would start with our equilibrium expression. So in this case, K would equal the concentration of NO2, and once again, I do need to square it because of the coefficient, divided by our reactants, which is the concentration of N2O4. Again, the coefficient is 1, so I really don't need to put anything on there. At this point, all I have to do is put in my equilibrium values. So here, N2O4 is 0.055 and 0.06 squared divided by 0.055. And here, we should get what they have on there, I hope. Squared divided by 0.055. Looks like 0.065 would be our equilibrium expression here, our value. That is considered, by the way, a small value of K, which means when we reach equilibrium, we would expect to mainly have reactants present. Any questions on that there? All right, let's see here. All right, so why don't you write the equilibrium expression for this reaction here? Assume they're all aqueous. Efficient times the concentration of D, which would need to be squared because of the coefficient, divided by the concentration of A, also needing to be squared because of the coefficient, times B in this case. Any question on that one there? Okay. All right, so as I mentioned before, homogeneous equilibrium involves basically an equilibrium where everybody's in the same phase. So homogeneous means the same throughout. So here everybody's in the gas phase. Here everybody is aqueous, so they're all in the same phases. Again, we could write an equilibrium expression here for our last guy, H plus concentration, Cn minus divided by HCN in this case. And obviously, I think we did the previous one earlier as well. There is heterogeneous equilibrium, as I also mentioned, and in that case, you do have some in different states. So here we got some solid, and we have gas. Here we have liquid, gas, and gas. So again, as I mentioned before, things that are in the solid state and things that are in a liquid state, they basically will not interact in the equilibrium. So if we were to write the equilibrium expression for the first one here, it would be basically the concentration of O2 cubed, and we would not include this guy because it's a solid, and we would not include this guy because it is a solid as well. So this would be our only equilibrium expression. This would be a Kc in this case. Here on the bottom, our K would be our H2, and we would have to square it because of the coefficient, times our O2. Once again, here we're not going to include the water because it is a pure liquid. It remains relatively constant throughout the whole process. Its concentration really doesn't change all that much. Now, it is possible, yeah. Why is it not 1 over O2? It's products divided by reactants. So products go up on top and reactants go on the bottom. Yeah. Now, speaking of something like that, though, for example, if you had something like this, let's just say we had, I don't know, we'll just do this here. Let's just say you had something like this that maybe went to like a solid or something, right? So say you had a reaction like this, you need to write the equilibrium expression for this. Clearly in this case, because our products are all solid, nothing would go on here. In this case, you actually would use 1 over the reactants. And the K in this case would be 1 over A cubed in this case, if you didn't have any uh, products that would be included. You just do 1 over the reactants in this case. Just like we did up here where we didn't have any reactants, basically it would just be the products that are sort of part of it. Question on that there. Yeah, I mean, it kind of depends, but it probably might be a small one in that particular case. Um, and there are some K values that are, for example, considered small values just in general. They're usually very small. For example, in this chapter, we're not going to go too much into it, but there's a K value known as KSP, and KSP stands for solubility product. And this is the equilibrium for things that are, if you remember, like your solubility rules, these are things that are insoluble, normally based on solubility rules. So if you remember, for example, you have like chlorides, bromides, and iodides. They're soluble in everything except for like silver, lead, and mercury. So if you had something like silver chloride, which based on solubility rules will make a solid, even things that make a solid, for example, will break apart a little bit into its ions in solution. So you have just a little bit of it breaking apart into those ions. But because it is mainly going to be this guy staying together, this type of value, for example, KSP values are typically very small values, like to the minus 16 or like to the minus 36 or something like that, times 10 to the minus 36. They're really, really small because they're essentially made for things that are essentially insoluble and going to stay together, and they typically find a reactant site. By contrast, you can make something that's known like a complex ion. and a complex ion is super favored to occur. And if you get something like, say, ammonia makes a complex ion with a lot of metals, like silver, for example, if you threw some ammonia in here into your silver chloride that's a solid, the formation of silver and ammonia want to come together so much that your solid will actually dissolve and release the silver into the solution, and where it can then hook up with the ammonia. And that sort of formation is very, very much favored at that products, that complex ion would be made in the product side, that those type of values, which are known as KF values for complex ions, those values are typically super large values, usually like to the 50s or like 34s, times 10 to the 34 and stuff like that. So really, really big sort of values. So there are certain things that just have small values. There are certain things that, sort of have large values. And that comes into a lot of play in terms of how you do certain calculations involving equilibrium that you'll learn about when you go to 1B and you take all that good stuff there. All right, so as I mentioned before, the position of heterogeneous equilibrium does not are affected by solids or liquids. So once again, as I mentioned before, we do not include anything that's a liquid. Anything that's a solid is left out of the equilibrium expression. So here is another sort of KSP type situation. We have this solid goes to aqueous ions. In this case, it would be just the product side here, as those guys are aqueous. Again, this being a solid would not be included in the expression, and that would obviously give us our D that's there on the bottom. All right, so the last thing we're going to really talk about here in this chapter is Le Chatelier's principle. And the idea of Le Chatelier's principle is pretty much this. It is you have a system that's at equilibrium. So in Le Chatelier's principle, you have this system that is at equilibrium, and you decide, I would like to screw it up, basically. I would like to do something to cause a stress to that system. Now, what are some stresses that you could do to a system? You could do something with the concentration. You could either add or remove concentration. That is something that can mess up an equilibrium. You could do something with volume and pressure. Could kind of screw up an equilibrium. You also could do something with temperature. Either increase or decrease the temperature. You could also add a catalyst. So these are different things that you could do to a system that is at equilibrium that will kind of screw up the equilibrium. As I mentioned before, what will happen though is even if you do something to it, that reaction will want to get itself back to equilibrium. So like I said before, it can kind of self-correct itself. The way it could correct itself is you have a system at equilibrium, you mess it up, it will want to return to equilibrium, that system. And there's basically three options that could occur in terms of it being able to get back to equilibrium. Sometimes people refer to it as it will shift to the right. And if it shifts to the right, you're basically going to make more products. It will shift to the left. And if you shift to the left, you'll make more reactants. And lastly, even though you did something to it, there is actually a few situations where nothing's going to really happen. There's going to be no change. So the idea here again is we have a system at equilibrium. We screw it up. The system will either go to the left, go to the right, or no change to get itself back to that equilibrium condition of the rate of the forward direction will equal the rate of the reverse direction. All right, so let's take a look at each of these here and see what is going on or what happens in each of these situations. The first thing we're going to talk about is concentration. So let's talk about that. So as I mentioned before, you could either add more concentration, and when we add more, what happens is it will shift away from the side you added it to. Now you may be wondering, what are we talking about sides? And what we're talking about in terms of sides are the actual balanced equation. Yeah. So your reactants and your products. So when you look at the balanced equation and we talk about adding something to the left-hand side, we're adding more reactants. Or we're adding something to the right-hand side, we're adding more products. So if you add something, it will always shift away from the side you added it to. AA is a good way to remember that. Add away, right? We'll do that. If you remove something, it will actually shift towards the side you removed it from. So you can kind of think about it one way or another, but sometimes the way you can think about it is if you remove something, you create like a hole on that side, so it's got to go towards the hole to fill it. So if you remove reactants, it will go to the reactant side. If you remove products, it will go to the product side. How can we add more of something? That's pretty simple. You just go to the shelf and pick a reagent that has it in it. You just dump it in, right? So for example, if you want to add sodium, you go grab a bottle of sodium chloride and you add it in. You just added sodium, right? Or you want to add chloride. You dump your sodium chloride in. You're also adding chloride as well. To remove something, that's a little bit more tricky because we were usually talking about solutions where things are floating around. You can't just reach in there with your hand, hopefully, into the beaker and grab out some ion. So one way that we can very commonly remove something is to add something to the equilibrium that makes a precipitate, which is a solid. So for example, if we had chloride floating around in that solution and we wanted to remove chloride, we could add some silver nitrate, which is silver. The silver and the chloride would come together and make that white solid of silver chloride. That essentially would be like removing chloride from that solution. So that's a very common way you can remove something from a solution. You add a reagent that will precipitate out something that's floating around, and you can very easily do that. Another way that you could do it is something that you may not be able to visually see occur, but if you had, for example, a beaker that had hydroxide in it, you could add an acid, and an acid is H plus. H plus and OH minus will make water, which is a pure liquid, also not included in the equilibrium, and that would be essentially like removing hydroxide. So those are two very common ways. For example, you could remove something from a solution, make a precipitate and precipitate out one of the ions, or you can add either H plus or OH minus, depending on what you got in your solution, and perhaps make some water to get rid of those things. Any questions on that there? So let's just say, for example, here we had this side is the reactant side, that's the product side. And we had our award-winning stick figures here. This is advanced stick figures, they have faces. And let's just say we're at equilibrium at this point. So we're at a nice equilibrium position. And let's just say that we decided to add more products in this case. So somebody hops on the right-hand side here. When that person hops on the right-hand side in this case, this is what's going to happen. And that's not so good for the guy on the left. To fix this situation, do we need more people on the right or more people on the left? Yeah, we need more people on the left, right? So we add it over here to the right. It will shift away from where we added it. And now it will be able to come back to equilibrium at this point. And everybody will perhaps be happy, maybe. And we're now back to equilibrium position. So again, in this case, added more products, shifts away. Now, let's say we did the same thing over here. And let's say that this guy decides he's going to hop off. So we're going to remove some products here. When that guy hops off, this is what's going to happen. Again, in this situation, to fix this problem, we actually need to go towards the side we removed it, kind of like filling the hole, if you want to think about it that way. This guy will then come back to equilibrium. And now everybody is happy here. Any questions on that there? All right, so let's take a look here. So let's say we had 2a plus 3b goes to 4c. Let's say I added C, I removed B, I added A, I removed C. What will happen in each of these cases? Will it shift to the right? Will it shift to the left? Or will there be no change? So take a moment and decide. Okay, let's take a look. So here we're going to add C. So C's over here. When we add, it always goes away. So AA. So we added to the right-hand side of the equation. It should shift away from it and should cause it to go to the left. What's really happening in this case is by adding more products, we're going to have more products than reactants. And that's going to cause the reverse reaction basically to occur. We're going to shift to the left there. We're going to remove B. So when we remove, it actually goes towards the side we removed it from. So it will actually go to the left as well. What's really happening in this situation is when we remove we remove B, we now have more products than reactants. So again, it's going to cause the reverse reaction basically to occur, and it's going to head in that direction. We're going to add A. A is on the left-hand side here. Add away. Going to go away from the side we added it to, and it will shift to the right in this case. Again, in this case, we will have more reactants than products. It's going to cause the forward direction to occur. Lastly, here we're removing C. C is a product. That's going to cause us to have more reactants than products. It's going to go towards the side we removed it from to fill the hole, if you want to think about it that way. Any questions on any of those there? Okay. All right, so that is concentration. Let's then talk about a couple of the other things. The next sort of topic there is pressure and volume. And oftentimes, pressure and volume are tied together. It is related to our friend Boyle and his law. If you remember, if the pressure goes up, the volume goes down. And what happens in this situation is the pressure is starting to go up, so we want to bring it back down. So in a smaller volume, we would actually need less gas molecules. So it will shift to the side that has the less gas molecules. That depends on the equation you're looking at. So you have to look at the equation and add up everybody that's got a G next to them, right? And add up how many you have of those. If the pressure goes down, the volume will go up. And now in this larger volume, we will actually need more gas molecules. I personally like to think of it in terms of volume. Small volume, less gas molecules. Larger volume, more gas molecules. So if you understand the pressure volume relationship, I would always think about it in terms of volume, and it matches the volume. So again, small volume, less gas molecules. Larger volume, more gas molecules. Any questions on that there? The next one is temperature. Temperature works the same as concentration, which means if you increase the temperature, it will shift away. And if you decrease the temperature, it will shift towards it. Now, how do you know which side temperature is on? It has to do with what type of reaction you are dealing with. Is it an exothermic or endothermic reaction? So if we have a exothermic reaction, energy is released, and we think of temperature or energy as a product in this case. Remember, our delta H would be negative in this case. So you would have something like this. We would think of heat and energy as a product. If you have an endothermic reaction, energy is absorbed, and we think of it as a reactant. Remember, our delta H is positive in an endothermic reaction, and that would be like heat plus our reactants. Go to our products in this case. So for temperature, you have to think about, is it exothermic or endothermic? I would say that this is probably, in most cases, how that would be displayed to you. A lot of times they'll give you the equation, and at the end of it, they'll go, the delta H of this reaction is positive or negative, and that will allow you to determine if it's exothermic or endothermic, and then it will basically either shift away or shift towards it, depending if you increase or decrease the temperature. Any questions on that there? Now, lastly, the last thing that can affect it is a catalyst, which again, as we talked about, is not a reactant, not a product. It does not get used up. It just makes the reaction occur faster. So if you add a catalyst, it will actually cause no change to occur. So that's one of the few things that will cause no change to occur. A couple other ways that you could get a no change is, for example, if you add like a noble gas. Noble gases are chemically inert, which means it will not cause a change. And really the third way that you could get a no change is this situation here. When you go look for the more gas molecules or less gas molecules, and you got the same number of gas molecules on each side. So that's like a push. It's kind of a no change situation that can occur. So that's also a situation where you could have a no change. Any questions on that there? All right, so let's try one here. Let's go with 2A plus B goes to 4C. Let's go with the delta H is negative 125 kilojoules. All right, so for each of these situations, again, will it shift to the left, shift to the right, or no change here? All right, we're going to add C. We're going to increase the temperature. We're going to decrease the volume. We're going to add B. Going to remove A. We're going to decrease the pressure. We're going to add a catalyst. We're going to remove B. All right, so for each of these, what will happen? Again, when we add, it goes away from the side we added it to. So we're going to add to the right. It's going to shift it to the left, away from it. Again, that's going to cause the reverse reaction to occur because there's more products than reactants. We're going to increase the temperature. So increasing temperature has to do with what type of reaction. So here we can look at the delta H value and it's negative. That negative sign tells us it's exothermic. That means that heat and energy is considered a product. Now we know it's a product and we're going to increase it. So again, that'd be like adding more products. So it's going to shift away from the product side and it should shift to the left in this case. Any questions on that there? I'm going to decrease the volume. When I decrease the volume, it has to do with the pressure. The pressure is going to actually go up. And in that small volume, I actually need less gas molecules. So small volume, less gas molecules. Don't overcomplicate it. That's a G, that's 2. That's a G, that's 1. So that is 3 gas molecules there on the left. That's a gas, that's 4. 4 gas molecules on the right. So in this case, the less number of gas molecules is to the left in this case. Any questions on that there? I'm going to add B. B is a reactant. I add away, so it should shift away from the reactant side to the product side. And again, in this situation, what's really happening is I now have a lot more reactants than products, so it's going to cause the forward direction to occur. Removing A is a reactant. When I remove A, it's going to go towards it to fill it, and it would shift to the left. When I remove A, I have more products than reactants, causing the reverse reaction to occur. If the pressure goes down, that means that my volume has went up, and I now have a larger volume. And once again, in the larger volume, I need more gas molecules, which in this reaction is to the right. When I add a catalyst, that's going to have no change. And lastly, when I remove B, which is a reactant, it is going to go towards the side I removed it from. Again, by having more products than reactants, it's going to cause the reverse reaction to occur in this case. Any questions on any of those there? All right, so as we talked about, changing concentration, add away. If you remove it, it will go towards that side. Again, changes in volume is related to pressure a lot of times. Volume is really a good way to look at it. Larger volume, more gas molecules needed. Smaller volume, less gas molecules needed. Exothermic, endothermic, once again, will tell you if it's exothermic, heat is a product. If it's endothermic, then heat is a reactant. Like I said before, probably the most common way is the delta H value given to you, positive or negative. Or they could write it actually into the equation. And again, if you see a heat value on the product side, it's a exothermic, and if you see a heat value written on the reactant side, it's an endothermic. All right, let's take a look at this one here. Consider the reaction. How many of the following would lead to a shift in the equilibrium towards the reactant side? So why don't we just go through them and see what will happen. In this case, we're going to remove CO. So CO is a product. When we remove it, it should go towards it, and it would cause the equilibrium to shift to the right. So that's going to shift to the right. So that definitely is not going to the reactant side. If we add more O2, O2 is a product. When we add it, we'll go away from the side we added it to. So that should cause it to shift to the left. So that would do it, right? If we remove CO2, like causing a hole over here on the left-hand side, when we remove it goes towards it. So that will cause it to shift to the left. So that also would cause more reactants. And lastly, increasing the pressure by decreasing the volume. So again, small volume, less gas molecules. There are 2 gas molecules there. That is 2 gas molecules, and this is 1 gas molecule. Grand total of 3 gas molecules. Less number of gas molecules is to the left here. So the 3 that actually will do it is 2, 3, and 4 up there will cause the equilibrium to shift to the left. Any questions on any of those there? One method for the production of hydrogen gas is through this endothermic process. How many of these would decrease the hydrogen gas formation? So let's again go through them and see what will happen. If I added H2O to this, H2O is over here. Add some reactants to shift away and go to products. That should actually increase the H2. By the way, I'm adding water in this case because in this case, the water is in the gas phase, not liquid. So it is included, yeah? So we do include that in there. The volume of the container is doubled. So that means the volumes can get larger, which means we need more gas molecules in this case. On the left-hand side here, 2 gas molecules. Right-hand side, 1 plus 3 is 4 gas molecules. So that should cause it to shift towards the more gas molecules, and that would be to the right. CH4 is removed. CH4 is a reactant. That's going to cause a hole on the reactant side, and it's going to shift towards it. And lastly, the temperatures increase. This is an endothermic process, which means heat is a reactant. And if we increase a reactant, it's going to shift away from it. So in this case, it's actually number 3 that would cause the amount of H2 to decrease in this case. All the other shifts would actually increase the amount of H2 that you would have as they are all going to the product side there and making more H2. Any questions on any of those?